Hi, my name is Sam Neal, and for my thermodynamics final project, I'm going to be looking at a real refrigeration cycle. We use refrigerators in our daily lives, and we rely on them 24/7 to keep our food cold. For this project, I will examine real-life working conditions of a refrigerator in my apartment. The fan motor bearing is bad, and I want to see how much this, along with age, affects the coefficient of performance. My suspicion is that because the fan is not pulling as much heat away from the condenser coil, this will lead to a reduced efficiency and a reduced cooling capacity. So as you can see in this video, the condenser fan is making a lot of noise, and I saw this as a problem. I started by opening up the back of the refrigerator, and this gave view to the compressor, the condenser fan, and the condenser itself. Then I opened up the inside of the freezer to look at the evaporator coil. I needed to do this so I could take temperature measurements on the tubes going in and out of the evaporator coil. You can also see the evaporator fan in this picture. For this refrigeration cycle, I will be using this model. This is a simple vapor compression refrigeration cycle on a PV diagram. We are assuming that state 1 is a saturated vapor and state 3 is a saturated liquid. I made this diagram of the whole cycle that shows everything in clear detail. As you can see, the refrigerant starts at state 1, is compressed by the compressor to state 2. The refrigerant then goes through the condenser coil where it rejects heat to the environment and ends up in state 3. From state 3 to 4, the refrigerant goes through a capillary tube, which is essentially a valve or a throttle, and that simply decreases the pressure by a significant amount. Then the refrigerant goes through the evaporator coil, where heat is absorbed from the inside of the freezer and refrigerator. I started off my measurements with looking at the electrical power inputs, using this watt meter pictured here. I found that the refrigerator settled out to around 70 watts of power draw. I also saw that in a certain state of the refrigerator's power cycle, it would have the evaporator and condenser fans on with the compressor off. This drew about 6.5 watts, so since the condenser and evaporator fans are similarly sized, we'll say these drew 3.25 watts each. One interesting thing that I found about this refrigerator is that it only has one evaporator fan, but it controls two different temperature zones. It does this by directing only some of the air down to the refrigerator, and most of it keeps up in the freezer. To start taking temperature measurements for the different stages of the cycle, I got this temperature reader, which would log values over time. And I would attach this to different points of the refrigerator to record the temperature values. The duration of time that I left the temperature probe on and recording depended on the specific stage I was measuring. For example, for ambient temperature here, I didn't need to wait very much time because the ambient temperature is pretty constant. It only fluctuates due to the air conditioning system in my house. However, for things like the air coming out of the evaporator and the condenser, as well as the temperatures of the refrigerants in each stage of the process, I would let this go overnight because the refrigerator is constantly turning on and off. So this is how I measured the air coming out of the evaporator and condenser. This is a picture of the evaporator output, and I just taped on the temperature probe there, and this is the data I got from that. Since we have two primary values here, the peak values and the trough values, I chose to take the lowest values for the parts of the refrigerator that should be cold and the highest values for the parts of the refrigerator that should be warm. So since this is the evaporator output, it should be cold, and I'm going to take the average of the minimum temperatures, which is going to be negative 22.44 degrees Celsius. Similarly, for the condenser, I got a peak value average of 28.36 degrees Celsius. This is what I got for stage 2, which is the output of the compressor. We have a peak value of 34.14 degrees Celsius. And then for stage 3, we have a peak value of 31.54 degrees Celsius. For stages 1 and 4, I measured directly off of the evaporator, and as you can see, this is the process of getting to the evaporator coil. Once I attached the temperature probe to one of the copper tubes coming out of the evaporator coil, I reassembled the refrigerator with the probe wire sticking out and let the refrigerator run through its cycles. At first I wasn't sure which of the copper tubes going into the evaporator was state 4 and state 1, so I ended up just measuring the temperatures blindly and figuring out which one got to a lower temperature. Since heat is absorbed in the evaporator coil, state 4 should be at a lower temperature. This is what I got for stage 1. I have a peak temperature of around negative 6.5 degrees Celsius. One interesting thing to note here is there's a big spike in the beginning, and I believe that's because of the defrost cycle. When an evaporator coil is running too long, it can frost over, and the only way to get rid of this is to run an electrical coil for some time to heat it back up. But I was still able to record relevant peaks in this graph. And here are the recordings for stage 4, where I got a minimum value of negative 25.13 degrees Celsius. So putting that all together, here's everything laid out, all of the relevant values, and from this data, I did some calculations. I neglected changes in potential and kinetic energy for all of the models. I assumed the compressor, condenser, and evaporator coil were adiabatic outside of the heat transfer between the fluids. And I did control volumes and energy balance equations for each. I also assumed that the valve, the capillary tube, is isenthalpic. I ended up having one too many unknowns to solve this system, so I found a value for the mass flow rate of the refrigerant online, which can be found in my sources. I assumed this to be 1.661 e to the negative 3 kilograms per second. So from all of this, I got the enthalpies for each stage, and this allowed me to find the rate of heat extracted from inside the refrigerator and freezer. This allowed me to find the coefficient of performance, since I knew the amount of work input in electrical work, and that was around 0.8, which is less than 1, so I considered the cycle pretty inefficient. Most refrigerators should be running above that. So in conclusion, I learned a bit about refrigerators, and I think they're pretty cool, but they are more complicated in real life than they are on paper. I also concluded that the coefficient of performance was less than 1, so this unit is operating inefficiently, and my apartment maintenance team should probably replace it before the fan finally dies to high loading from friction on the bearings. And here are my works cited. Thank you for watching.